First, in order to simulate the directed torque control of induction machine, we set up this circuit in MATLAB or Simulink. Here we have the input reference torque, which is summed with estimator feedback. Then we have two relays. Relay 3 has switch on point set at higher band torque, while switch off point is set at 0 middle band. For relay 4, the switch on point is set at middle band and switch off point is set at lower band. Both relays are summed and connected to the mux. We also have reference flux input. It will determine the difference between reference flux and flux from estimator. The frequency reference value is defined in the motor parameter Lorenzo M file. From the coding, all parameters are defined and is run to send the values to workspace. The reference flux is summed together with flux from feedback estimator as can be seen here. For relay 5, the switch on point is set at positive flux band and switch off point is set at negative flux band. This will go into the same mux as reference torque. The last input to the mux is from the sector detector. The coding for the sector detector is designed based on the tree diagram on the right. As you can see, the if-else command in the coding follows the decision flow based on the tree diagram. The torque error status, flux error status, and flux status are marked into the lookup table. In the lookup table, we must first define T-stat, F-stat, and stator. We also have to initialize switching status of SA, SB, and SC to 0, 0, 0. For example, in sector 1, if the flux error status and torque status are both 1, the output will be 1, 0, 0. If the flux error status is 0 and the torque error status is 1, the output will be 1, 1, 0. The same process also applies for the other 5 sectors and the rest of the table. From the lookup table, we can generate SA, SB, and SC. In subsystem 6, the switching signals will go to these equations and generate real and imaginary values of voltage. As seen here, the real and imaginary voltage will be connected to the estimator as well. In the induction motor subsystem, the VSD and VSQ will be applied to this transfer function. The calculation output is then went through another series of equations. And this equation will produce TE, WM, ISD, and ISQ. The current value obtained from induction motor will also be sent to the estimator. In the next subsystem, ISD and ISQ are derived to obtain IA, IB, and IC. From the block diagram, we can see that it is derived based on the equation above. Next, we will go to plot selector. In this part, the plot selector function is to select the plot that we want to observe in the GUI. We have three switches, where switch 1 is connected to real flux and IA. Switch 2 is connected to imaginary flux and IB, while switch 3 is connected to real voltage and IC. Constant 0 is set here to switch off motor.
Now we are going to implement the DTC of induction motor using Flexi-Drive system. In the screen, we can see the control desk interface. Here there are several buttons that are used to control the motor from this computer alone. So for our first button is the activation of DTC. From here, we can either select the start or stop the motor. For the reference torque, we can adjust the value using the knob continuous adjustment. We can see that this knob is arranged from 3 to -3. We can also manipulate this value by using step change. When we click low torque, it is set at 1 while large torque is set at 2.5. Then we set the positive torque at 2 and for the negative torque we set at -2. As for plot selection, we use the plot 1 to analyze the flux locus of motor. For plot 2, we want to analyze the change of speed from low torque to large torque, as well as the effect on the torque, current, flux and torque error. For plot 3, we want to analyze the effect of changing from negative torque to positive torque instantaneously. There is also the flux hysteresis band where we control the gap between the upper band and lower band. Next, we also have to have the torque hysteresis band to control the upper band and lower band of torque hysteresis. To run the motor, click Start. Click Stop to stop the motor.
Ni last toggle. Kasih dia beza, nampak beza sikit.
Choose plot 1. As you can see at flux hysteresis band, there is a toggle button that is used to control from small, medium and large band. Now the flux band is set at the smallest bandwidth and this is the effect on the flux. As the smallest hysteresis band, we can see that the flux locus has a smooth circumference and no visible vector. Now, when we change the bandwidth to the middle band and check for change in the flux locus. Here we can see that the locus is no longer round and has a few visible vector components. Now we will adjust the bandwidth to the highest band, where upper band is set at maximum while lower band is set at minimum. Now we can see the flux locus is unsmooth while visible vector components around its edge. At the highest band, we can see that the resembles the flux control using hysteresis comparator as shown on the right. So this is the result obtained when we change from positive torque to negative torque. At the middle part, we can see that the torque drops instantaneously from 2 to -2. This is done to reduce the reference angle between stator frame and rotor reference frame. When we zoom into the oscilloscope, we can see the flux decrease rapidly and increase back to original.